Okay, hello everyone. Today we will learn hypothesis testing part 4. Let's move on to chapter 10.8, small sample hypothesis testing for mu and mu1 minus mu2. Actually, the testing procedure is very similar to that we learned for the large sample hypothesis testing, but the only difference is the test statistic that we will use. So let's consider this situation. Assume that y1 to yn follows normal distribution with mean mu and variance sigma square, and consider we are interested in testing something like this. The null hypothesis mu is equal to mu0 and under the null hypothesis, what would be the underlying distribution about this one? And from this underlying situation, what we know is what we can calculate is like y bar and also s square. That's what we can calculate from the sample y1 to yn. So and these are sufficient statistic, and with these sufficient statistic, the what we can derive is the t distribution. So if we define this way, then we know this one follows t distribution with n-1 degrees of freedom. So we are going to use this one as our test statistic, and if our alternative hypothesis is mu is greater than mu0, then how we can select the rejection region. So when we can reject this null hypothesis, so if the situation, if true mu is greater than mu0, then probably we are going to have larger amount of y bar. So the rejection region should be a large value of t. So if we observe large amount of the t, then it's the evidence that the true parameter mu is greater than mu0. And so with t distribution, we can calculate probability of our test statistic is greater than t alpha equals alpha, then we can select this one as our test threshold decision rule. And if we calculate our test statistic t, and if it is greater than t alpha, then we can reject the null hypothesis and accept that alternative hypothesis that mu is greater than mu0. So yeah, and if we draw the picture, let's say this is t distribution, and let's say we are interested in testing alternative hypothesis of this, and under the null hypothesis, mu is mu0, and what we observe is that oh, okay, so this is t distribution, so mean is 0, and we can calculate the value t, and so we probably calculate t, and this is here. And if the test statistic t is greater than t alpha, this is t alpha, and the area here is alpha, and if the test statistic t that we calculated is greater than t alpha, then we will going to reject the null hypothesis and accept the alternative hypothesis. And that's the procedure we will going to do. So if we are doing the hypothesis testing, if you are not very familiar, remember these steps. And do one by one. Then it's easier. So in step 1, you firstly need to set up your hypothesis and determine the level of significance. Usually you can find this step 1 from the question itself. So after reading the question or after reading the exercise problem, you will discover the underlying hypothesis. Something like the null hypothesis and the alternative hypothesis. And and the step 2 is select appropriate test statistic. So in this case, if you are interested in uh, about the one sample mu, small sample test for mu, then it's the test statistic is this one, and mm, and the step 3 is set up the decision rule. So think about the decision rule, and they are described in here. And step 4 is compute the test statistic, and using the decision rule, you conclude at step 5 and write your answer. That's user steps for the hypothesis, for the any of the hypothesis testing problems. So for every hypothesis testing problems, think this way, and you will probably you will find your solution not very difficultly. It's not very difficult. Okay. Let's move on to example 10.12. Example 8.11 gives muzzle velocities of 8 shells tested with a new gunpowder, along with the sample mean and standard deviation of these. And the manufacturer claims that the new gunpowder produces an average velocity of not less than 3,000 feet per second. And do the sample data provide sufficient evidence to contradict the manufacturer's claim at the 0.025 level of significance? So the step 1 is set up the hypothesis, and the hypothesis that we want to say is that we want to find the evidence to contradict the manufacturer's claim. And so for H0, manufacturer claims that our mu is not less than 3,000. So a manufacturer's belief is mu is greater than 3,000. And actually we want to test the manufacturer's claim, the contradiction of the manufacturer's claim. So our alternative should be mu is less than 3,000. And the contradiction of manufacturer's claim is true or not. That's what we want to test. So our alternative hypothesis is this, and the null hypothesis is mu is equal to 3,000. Okay, and the alpha is 0.025. So this is what we want to test. And what would be the test step 2? And in step 2, we need to decide the test statistic. And in here, we have 8 samples. So we have small sample size. So we will do the t-test. Our test statistic t is y bar minus mu 0 divided by square root of s squared divided by n. And this will follow t distribution with degrees of freedom 7. Okay, and so in step 3, we should decide the rejection region. Rejection region is that if we want to have the evidence of this alternative hypothesis, then rejection region should be less than some amount. So this should be, rejection region should be t is less than equal to t alpha. So and in here the t alpha is this is t distribution, and this is alpha of the t distribution. So yeah, so if you calculate the next thing, step 4 is calculate t and t alpha, and so you plug in all the numbers here and calculate the value t, and also you should calculate the minus t alpha. That's what we did here using R. So we calculated minus t alpha, which is minus 2.36, and also the calculation of t, it is done by this. And so what we do is our t is minus 2.96, and this is less than minus 2.36. So we reject the null hypothesis, and the alternative hypothesis is true. So our conclusion is that reject H0, the null hypothesis, and alternative hypothesis is true. So so we have sufficient evidence to contradict the manufacturer's claim with level alpha equals 0.025. That's what we can conclude from this hypothesis testing. Let's move on to next example problem. Example 10.13. What is the p-value associated with the statistical test in the previous example, example 10.12? Here, this is a t distribution, and actually, let's solve it using the graph. So this is a rejection rule, and the test statistic minus 2.996, that's what we calculated. And but for the p-value, we want to calculate this area. So what we want to calculate is that the t is probability of t is less than minus 2.996. This is what we want to calculate, and using R, we can calculate it this way. So since this one, this t distribution, the degrees of freedom is 7, so we can calculate it this way. This is 0.01, about 0.01. So this is the p-value that we calculated. Now let's move on to two-sample case. The hypothesis testing for mu1 minus mu2. Now we assume that we have two samples, two population samples. So the first population samples are y11 to y1n1. They follows normal distribution with mean mu1 and standard deviation, this one. And we have second group y21 to y2n2, and this one follows normal distribution with mean mu2 and variance sigma square. If this is the case, let's consider the hypothesis. The H null is mu1 is equal to mu2 under the null distribution, and the alternative case would be y1 is greater than y2, or y1 is less than y2, or sometimes y1 is not equal to y2. And what would be the test statistic for this case? And previously, for the large sample case, what we learned is that this would be y1 bar minus y2 bar divided by square root of s1 square divided by n1 plus s2 square divided by n2. And actually here, in our assumption, we have same variance. So we use the pooled standard deviation, so SP. So we will use pooled standard deviation estimator, and that's this one. So and actually this pooled standard deviation is actually you have all these samples together and estimate the standard deviation, the pooled standard deviation. That's this one. And then this one, previously this one follows normal distribution. However, if we do not have enough sample, this one follows t distribution with degrees of freedom is n1 plus n2 minus 2. And so we were going to use this t distribution to do the inference for this hypothesis testing. Okay, so if our alternative hypothesis is mu1 is greater than mu2, then how we can select the rejection region? So if mu1 is really greater than mu2, then we would observe the large t. So if we observe large value of t, then um, it would be inside of the rejection region. If we observe large amount of t, that's the case for the alternative hypothesis case. So what we take is, if t is large enough, then it would be the rejection region. So we take the rejection region this way. T is greater than T alpha, where the probability of T is greater than T alpha is alpha, which is our type 1 error rate alpha. Okay. And again, if you are not familiar with hypothesis testing, remember these steps. Step 1, set up hypothesis and determine the level of significance. And step 2, select the appropriate test statistic. And in this case, you are interested in comparing two population distributions. So we are going to use this t distribution, and also after decide your test statistic, the next step is set up the decision rule, which is finding rejection regions. And step 4, compute the test statistic. And step 5, you can conclude your conclusion. Okay. Okay, let's move on to example problem 10.14. Example 8.12 gives data on the length of time required to complete an assembly procedure using each of two different training methods. The sample data are as shown in table 10.3. Is there sufficient evidence to indicate a difference in true mean assembly times for those training using the two methods? So we want to test whether there is the evidence of a difference in true mean. Test at the alpha equals 0.05 level of significance. So the first step is set up the hypothesis, and the hypothesis is about the evidence of the difference in true mean. So our H0 is mu1 is equal to mu2, and our alternative hypothesis is mu1 and mu2 are different. Okay, so this is our hypothesis, and what would be the level of significance? This is 0.05, and the next one is set up the test statistic. And since we have only 18 samples in total, we would use the t distribution, and our t statistic is y1 bar minus y2 bar divided by pooled standard deviation times square root of 1 over n1 plus 1 over n2. And so we can calculate it using the formula. And also, what would be the rejection region? So the two-sided test rejection region for the two-sided test, the t should be very large or very small to reject the null hypothesis. So our rejection region would be t. Absolute value of t is greater than t alpha over 2. Okay. So this is our rejection region, and so the next thing is to calculate the test statistic and this one and do the conclusion. So I did it using R. So this is the calculation for the pooled SP, the standard deviation of the pooled standard deviation, and this one is the calculation of t, and this one is calculation of t alpha over 2. Okay, so what we observed is 1.64 is less than 2.11. So this is not inside of the rejection region. So our conclusion is do not reject the null. Do not reject H0. There is not much evidence that the difference in two mean is statistically significant with alpha level 0.05. Okay, so this is our conclusion. And let's move on to example 10.15. Find the p-value of the statistical test of example 10.14. And this is finding the probability of our calculated test statistic is the distribution of t is greater, the absolute value of t is greater than our observed value. And so this is the thing that we observe, and this is the distribution. So t distribution with degrees of freedom 16. This is the t distribution, and what would be the probability that we observe this? And this value is the statistic that we observed. This is 1.65. So the probability of absolute value of t is greater than 1.65. This is what we want to observe, and to do that we calculate one of these probability and calculate times 2, and that's this one. So we calculate the area of this one and then time multiply 2 to get the probability. So the p-value is 0.1192. So this is our approximate p-value for this problem. Let's move on to exercise problem 10.75. The tremendous growth of the Florida lobster industry over the past 20 years has made it the state's second most valuable fishery industry. A declaration by the Bahamian government that prohibits U.S. lobsters from fishing on the Bahamian proportion of the continental shelf was expected to reduce dramatically the landing in pound per lobster trap. According to the record, the prior mean landing per trap was 30.31 pounds. A random sampling of 20 lobster traps since the Bahamian fishing restriction went into effect gave the following result. Okay, and do these landings provide sufficient evidence to support the continuation that the mean landings per trap has decreased since imposition of the Bahamian restrictions? Okay, so we want to test whether the production is decreased or not. So the step 1 is set up the hypothesis. The hypothesis is mean is 30.31, and or alternative hypothesis is whether it is decreased or not, 30.31. And alpha level is 0.05, and the step 2 is to decide the test statistic. And since we have 20 observations, maybe this is not very large samples. So let's use t distribution, which is t is y bar minus mu 0, which is 30.31, divided by s standard deviation of the sample standard deviation divided by square root of n. And so and the what would be the rejection region? Rejection region should be t is less than minus t alpha. Okay, so the next step is to calculate, and we can use R. Put the data like this, and we can calculate mean and standard deviation. This line is the calculation of the t statistic, which is minus 0.64, and also this is calculation of p-value. Actually, I missed the calculation of t alpha, but this minus 0.64. This one should be more. Let me do this quick. Wait a minute. Let me do this quick. Qt. This is Qt of 1 minus 0.05, and degrees of freedom is 19, and so it would be minus 1.73. Minus 1.73. So this it would be minus 1.73, and so our conclusion is that we do not reject the null. Do not reject H0. Yes. Okay, so this is our conclusion, and our p-value is this one. You can calculate your p-value with this one, and also actually we can do this t-test more easily like this. If the data 1 is your data, then actually you can use your R function t.test to do the t-test. So if you go out around the world, so if you go out in the industry or academia, and if you graduate the university, then when you are doing t-test, then probably you are going to use this function. But for this class, this is mathematical statistics class, so I recommend using these methods throughout the courses, and after the graduation or after another project, if you have chance to use the t-test, then use this one instead. That's my recommendation. Okay. The homework for chapter 10.8 are these. Okay, let's move on to chapter 10.9, testing hypotheses concerning variances. So far we have tested about the mean parameter. What about variance parameter? So let's assume that our population y1 to yn follows normal distribution with mean mu and variance sigma square. And what about we are interested in testing about the variance? Like consider our null hypothesis. The sigma square is equal to sigma 0 square under the null situation. Then probably you would use the s square, and actually you know the related distribution using s square, which is the chi-square distribution, n minus 1 times s square divided by sigma 0 square. This one follows chi-square distribution with n minus 1 degrees of freedom. So you can use this distribution to the test. So if H alternative hypothesis is sigma square is greater than sigma 0 square, how we select the rejection region? So if we have large amount of sigma square, if our real sigma square is larger than this one, probably we will have uh, large amount of S square estimate. So if we have large S square estimate, then it is the evidence that the true sigma square is greater than sigma 0 square. So the rejection region would be our calculated chi-square value is greater than something. Actually, this is same as S square is greater than K. The rejection region is something like this, and this goes into the rejection region of this thing. Okay, and we can calculate the chi-square alpha using this probability distribution, and this is the situation is something like this. So this is chi-square distribution, and you can calculate alpha level rejection region using this table, and actually you can use Q-chi, P-chi, Q-chi, P-chi. Anyway, you can calculate this chi-square alpha using R, and just like before, and you can do the test, hypothesis testing. Okay. About the different alternative hypotheses, you can decide the level alpha this way. So this is your chi-square distribution, and you can have your alternative hypothesis like this. Sometimes your alternative hypothesis is sigma square is less than something, and or sometimes the sigma square is not equal to something. So for each of them, you can calculate the related probability. Sometimes this way, sometimes this way, or sometimes for the two-sided case this way. And so anyhow, you can calculate the values related to here, and you can calculate the you can do the decision based on your inference. Again, you can follow these steps. Step 1 is the set up hypothesis and determine the level of significance, and the step 2 is select the appropriate test statistic, and step 3 is set up the decision rule, and step 4 is compute the test statistic, and step 5 is making conclusion. This one always holds for any of hypothesis testing steps. So if you are doing some hypothesis testing, think this way. And for test of hypothesis concerning population variance, then your test statistic in step 2, this is chi-square distribution that you will going to use, and the rejection regions are described here, and yeah, that's it. Let's move on to example 10.16. A company produces machined engine parts that are supposed to have a diameter variance no larger than 0.0002. A random sample of 10 parts gave a sample variance of 0.0003. Test at the 5% level, which is alpha. This is our hypothesis. So this is our step 1. Define the hypothesis. Our H0 is sigma square is equal to 0.0002, and our alternative hypothesis is sigma square is greater than 0.0002. And the test statistic is, we know this from the previous slide, which is n-1 times s square divided by the sigma 0 square. which will follow sigma square chi-square distribution with n-1 degrees freedom, which is 9. And to do this alternative hypothesis, what would be rejection region? Rejection region would be our let's say this is chi-square statistic. The chi-square statistic should be larger than k. If we have larger amount of chi-square, which implies that our in the reality our sigma square estimate in reality sigma square would be large. That's alternative hypothesis situation. So rejection would region would be this, and also actually we can calculate this k using chi-square alpha, which is derived from the chi-square distribution, and this is 0.05. And the next step is to calculate everything. For this calculation, actually the q chi, so the area here is 0.95, so q chi is q 0.95, and with degrees of freedom 9 returns this value, which is 16.91. And what about our test statistic, the chi-square, this one? So n-1 is 9, S square is 0.0003, and our sigma 0 square is 0.002. So this chi-square statistic is 13.5, and this is actually less than 16.91. So our chi-square statistic is less than the chi-square alpha, which is 16.91, and so we cannot reject the null hypothesis. So our conclusion is to not reject the null hypothesis. This is our conclusion, and yeah, and let's move on. Next one is example 10.17. Determine the p-value associated with the statistical test of example 10.16. Previously, the test statistic that we calculated is 13.5. So what we'd like to calculate is the area here. Here is 13.5. So using R, so yeah, that's what we want to calculate. And using R, we can calculate this way. So using p chi-sq, using our p chi-sq function, you can calculate the area here. And actually, to calculate this area, it is 1 minus p chi-sq of this one. So the answer is the probability of your chi-square distribution, chi-square statistic is greater than 13.5, is 0.1413, something like this. Okay. Let's move on to example 10.18. An experimenter was convinced that the variability in his measuring equipment results in a standard deviation of 2. 16 measurements yield S squared equals 6.1. Do the data disagree with this claim? Determine the p-value for the test. What would be your conclusion if you choose alpha equals 0.05? So, we want to do the test about, so our H0 is sigma square is equal to 4, because standard deviation of 2, which is so variance is 2 square, which is 4, versus H1 is sigma square is not 4, and the alpha is 0.05, and our test statistic is n-1 S square divided by sigma 0 square. So this will follow chi-square distribution with degrees of freedom n-1, and the rejection regions would be, if this is the distribution, so these are rejection regions, 0.025 here, 0.025. Okay, so now let's do the test. And actually the problem is determine the p-value for the test. So if we calculate our test statistic, this one, if this is here, then you can calculate the area here. If the test statistic is this here, you can calculate this one, and the times 2. That's the p-value. So let's calculate this quantity first. So n-1 is where is n? 16 measurement. So 15. So 15 times s square is 6.1 divided by 4. This one is 22.875, and so your p-value is this part is 22.875, and if you calculate this area, since this is a two-sided test, you have the same area here. So this is you can calculate the area here and times 2. That would be the p-value. So this part is, if you calculate p chi-square of this one, you are calculating this area. Here this part is 22.875, and so 1 minus p chi-square of this thing will calculate area of here, and we have to double this area because this is two-sided test. So you are multiplying 2 here, and you get this number. So this is your p-value. Okay, let's move on to two sample cases. Assume that you have two samples, y11 to y1 and 1. It follows normal distribution with mean mu1 and variance sigma 1 square. And you have second sample, y21 to y2 and 2, and that follows normal distribution with mean mu2 with variance sigma square, sigma 2 square. And we are interested in testing sigma 1 square is equal to sigma 2 square or not, or we don't know, alternative hypothesis. But to do the test about this, what you know is sample variances S1 square and S2 squares. And actually, you know the related distribution, which is F distribution. So using S1 and S2, if you define this way, this one follows F distribution with degrees of freedom n1 minus 1, this one follows F distribution with degrees of freedom n1 minus 1 and 2 minus 1. And so you can use this F distribution for doing the inference about the sample variances. So if our alternative hypothesis is sigma 1 square is greater than sigma 2 square, the rejection region would be if we have a larger value of F, then if S1 square is larger than S2 square, which is a large F, that support this claim, sigma 1 square is greater than sigma 2 square, so that will support this claim. So the rejection region would be F is greater than K. So this is our rejection region, and actually this K can be calculated from the F distribution. So like this way. and you can decide alpha this way. And so this is our F distribution, and the rejection region is here, and you can calculate the F alpha using F distribution. And yeah, and let's move on. The steps for the testing sigma square 1 is equal to sigma square 2 is actually very similar as before, and you can just follow the steps, and the only difference is test statistic and the decision rule. And actually this one only talks about sigma 1 square is larger than sigma 2 square, and actually this one and the another alternative hypothesis, sigma 2 square is greater than sigma 1 square. Actually, they are same. If this is the situation that's happening, then you can just replace 2 with 1. Then you can use this one again. And also, there are another alternative hypothesis that sigma 1 square is not equal to sigma 2 square. And also, you can also decide the rejection region using this situation, just like before, because this is your F distribution, and then you can put your alpha over 2 from this side and alpha over 2 from that side. Then you can again do this kind of test, and this is not very difficult. I think you can do it using R, as we just did for the one sample variance case. Probably we will going have some. I will cover an example for this situation. Let's move on to example 10.19. Suppose that we wish to compare the variation in diameters of parts produced by the company in example 10.16 with the variation in diameters of parts produced by a competitor. Recall that the sample variance for our company based on n equals 10 diameters was here, and in contrast, the sample variance of the diameter measurement for 20 of the competitor's part was calculated like this. And do the data provided sufficient information to indicate a smaller variation in diameters for the competitor? So the hypothesis is H0 is sigma 1 square is equal to sigma 2 square, and H alternative hypothesis is sigma 1 is ours and sigma 2 is competitors, and the smaller variance in diameter for competitors. So our variance is greater than the other variance, competitors' variance, and the alpha level is 0.05. And the test statistic F is S1 square divided by S2 square, and if you calculate it, it's 0.003 divided by 0.001, which is 3. And actually this one follows F distribution with N1 is 9 and N2 is 20 minus 1, 19. Okay, and so also the rejection region is that F is greater than some amount. So the calculated F is greater than F alpha. So this is our rejection region, and now let's try to calculate using R. So the F alpha uh, with degrees of freedom 9 and 19 is here. This is 2.422, and we calculated 3. So 3 is greater than 2.4. So we will reject the null hypothesis, and so for the conclusion, we reject the null hypothesis. That's our conclusion. Okay. Let's move on to example 10.20. Give bounds for the p-value associated with the data of example 10.19. Use the okay. So actually we are going to use R, not applet. But to calculate the probability p-value, this is the F distribution, and the value that we calculated is 3, and we want to calculate the area here. So to do that, we can use R. So PF, the PF calculates the area here. So to calculate this area, that is 1 minus PF of this thing. So, and the resulting p-value is this one. So this is the result. And let's move on to example 10.21. An experiment to explore the pain threshold to electrical shocks for males and females resulted in the data summary given in table 10.4. Do the data provide sufficient evidence to indicate a significant difference in the variability of pain threshold for men and women? Use alpha equals 0.1. What can be said about the p-values? Okay, so let's define our test statistics. H0 is the sigma square 1 is equal to sigma square 2, and the alternative hypothesis is sigma square 1 is different with sigma square 2, and our test statistic F is S1 square divided by S2 square, and let's try it this way. 26.4 divided by 12.7, and actually it doesn't matter if you flip these values. It just matter of what distribution you are going to use. If you are using this way, this is the degrees of freedom is 9 and 13. So 9 and 13. So as long as you use the correct distribution, then it doesn't matter if you define this one as 12.7 over 26.4 or vice versa. And so this one follows F distribution. And what would be the threshold using alpha equals 0.1? So here there's threshold here and threshold here, and so you can have this threshold this way. So you have 5% here and 5% here. So the value here, since this one is quite large, the value of this one is 2.079, and so since this value is quite large, you will calculate this value, and to calculate this value you use QF, and 0.95 will give this value, and this is 2.714. And also you can also calculate this value if you put 0.05 here inside of QF function, but that doesn't need it. And you can compare this one and this one, and since 2.079 is less than 2.714, we cannot reject the null hypothesis. So our conclusion is that do not reject H0. And also we want to calculate the p-value. What can be said about the p-value? So in this case, you can calculate the p-value this way. So pf of 2.079, this is so this is our f distribution, and the area here is this one. And so the area of this side is 1 minus this one, and actually for the p-value for the two-sided test, we also need to consider the area of this side, which is this one times 2, and so that's 0.2235. So our p-value is this one. Okay. Homework for chapter 10.9 are these. So far, we learned about hypothesis testing for small sample sizes or for the variance component. And in the next lecture, we are going to learn about the power of test and Neyman-Pearson lemma, and also the likelihood ratio test. And that would be the finishing of the hypothesis testing. So let's see you next week. Thank you.